Welcome to our first video on acid-base equilibrium. We're going to describe acids and bases in terms of proton transfer. A proton is simply a hydrogen nucleus without its electron, just a bare proton, and so we label it H+. Historically, there are a number of definitions of acids and bases, and the first one that we want to talk about is called the Arrhenius definition of acid and base. And an acid is a species that will produce H+ or hydronium in water, and a base produces hydroxide, which we'll write as either HO- or OH- in water. You'll notice that those definitions are restricted to aqueous solutions because we're talking about how these acids and bases behave in water. A more generic definition, and in my mind more useful definition, is the Bronsted-Lowry definition of acids and bases, where we're going to define an acid very simply as a proton donor and a base as a proton acceptor. So here is a simple example. Here's HCl. We know that is hydrochloric acid, but HCl reacting with water to be in equilibrium then with the chloride ion and the hydronium ion. Notice that what's going on here is that the HCl is donating H+, so that H3O is converted to, that H2O is converted to H3O+. After the HCl loses H+, what's left is the chloride ion. Here is a generic representation of this. And again, there would be HCl, HA, our acid. There's my base, B, and we get A-. That's the acid without its proton. We'll see later we call that a base. And HB+, which is be the conjugate acid. Or we might find that our base has a negative charge. Symbolically, these are just the same. There's some difference in charges, and as we look at specific examples, we'll see cases of either one of those. Now, one of the advantages of the Bronsted-Lowry acid-base definitions is that they apply to both aqueous and non-aqueous solutions, so it's a more generic definition than the Arrhenius definition. And here's what we know. A Bronsted-Lowry acid has got to have a proton, an H+, that it can donate, that it can lose. A Bronsted-Lowry base must have at least one lone pair to accept a proton and make a bond. A couple of other definitions that come in play when we're talking about acid-base equilibria, and they're almost interchangeable, and that's amphoteric and amphiprotic. Technically, an amphoteric species is one that can act as either an acid or a base. Regardless of how we define it, we'd say, okay, if it's amphoteric, it can be an acid and a base. In the Bronsted-Lowry world, an amphoteric substance is also going to be amphiprotic. It can either donate or accept a proton. Let's look at this very important reaction that can occur between two molecules of water. You'll notice that one of them can accept a proton to become H3O+, and one can lose a proton to become HO-. But what they've done there is, again, it's simply proton transfer. We're transferring a proton from one water to the other. Here's another example of a amphiprotic species. Here is the bisulfate or the hydrogen sulfate ion. It can donate a proton to water to form hydronium and the sulfate ion, or it can accept a proton from water to become sulfuric acid and hydroxide. So it can either donate a proton or it can accept one, and therefore it is by definition an amphiprotic species. There are other amphiprotic species, and we'll discuss more of those later in the course. Now, when an acid acts as an acid and donates a proton, what's left is its conjugate base. or when a base accepts a proton, what results is its conjugate acid. Let's look. Here is an acid, HCl. Its conjugate base would be Cl minus. Notice that's just HCl, and we've removed H plus. Let's do it again. Here is nitric acid. If it's the acid, when it loses H plus, when it loses a proton, what's going to be left? That's correct, the nitrate ion. Again, notice that the difference between those two species is just the H plus. Now let's play this game backwards. If this is the base, what are we going to get when it loses, what is going to be its conjugate acid? Remember that the base is going to have one fewer protons than its conjugate acid. So if we've got NH3 as the base, that means that NH4 plus, pardon, I had a typo, that NH4 plus is its conjugate acid. Notice again, if this were to give up a proton, that's what we would get. So when we're going from base to acid, we add a proton. When we're going from acid to conjugate base, we lose a proton. Let's go with two more examples. Let's let water act as an acid. If water acts like an acid, what do we get? That is correct, hydroxide. And if water acts as a base, it accepts a proton. And so what are we going to get here? Once again, that's correct, the hydronium ion. Notice again the difference to go there. To go from here to there, we lose H plus. So that means this is our acid, and that is our conjugate base. Again, this conjugate acid is the product formed when we remove a proton. Pardon me, the conjugate base is the product formed when we remove a proton from the acid. The conjugate acid is what we get when we add a proton to the base. Now let's notice that the strength of the acid and the strength of the base are going to be inverse. Strong acids have weak conjugate bases. Weak conjugate acids have stronger conjugate bases. So weak acids have stronger conjugate bases. Stronger acids have weaker conjugate bases. And the equilibrium is going to favor the transfer of a proton from a stronger acid to a stronger base. So when we're done, we ought to have the weakest species possible. Again, think of that as going downhill. Something that's a strong acid is going to easily and well give up its proton. So that ought to be the thing that happens, and we form a weaker species, a weak conjugate base as a result. We looked at this reaction earlier. This is a very important reaction that occurs in all aqueous solutions, and this is called the autoionization of water. This very simply is just proton transfer between water molecules. So one water molecule gives up a proton to become OH minus, and the other one accepts a proton. So if we look at it this way, that's plus a proton, and going here is minus a proton. So we're just transferring a proton from one to the other. The equilibrium constant here is just going to be H plus times OH minus, which that equilibrium constant at 25 degrees Celsius room temperature has a value of 1 times 10 to the minus 14th. So that means there's not much of this reaction going on. That's a very small equilibrium constant. Again, notice liquid water doesn't show up, right? We just put that in with a factor of 1. So it's just the products. We're dividing by 1, so I just don't show that in the fraction. But there's Kw. This is a very important relationship. You will have access to that relationship at all times and access to that value but let's look at it. Now, when a solution is neutral, that means that H plus and OH minus are in equal concentrations. If I have more H plus, it's acidic. If I have more base than H plus, more hydroxide than H plus, then the solution is basic. Now, if we look at this math then, we say, okay, great. Kw, which is H plus times OH minus, that's 1 times 10 to the minus 14th. If it's neutral, then H plus is equal to OH minus, and each one of those then is going to be 1 times 10 to the 7th molar. Ten to the minus 7th times 10 to the minus 7th is 10 to the minus 14th. And that's a neutral solution. Now, we don't want to have to talk about acid and base concentrations in terms of these very, very small numbers. And so what we do is go to a logarithmic scale where we're going to define the pH. And we define pH as the negative logarithm of the hydronium ion. And again, doing an inverse relationship, that means that the hydronium ion can be found by taking 10 to the minus pH. So let's consider this. If we're in a neutral solution, if we have a neutral solution, that means that the hydronium ion concentration is 1 times 10 to the negative 7th. The negative logarithm of that number is 7. So that means a neutral solution is going to have a pH of 7. If the concentration of hydronium is greater than 10 to the negative 7th, then the pH is less than 7. And if the hydronium concentration is less than 10 to the negative 7th, then the pH is going to be greater than 7. So again, acidic solutions, pH less than 7. Basic solutions, pH greater than 7. And let me tell you something here, that there's a common misconception that the pH scale runs from 0 to 14. Theoretically, we can have negative pHs. Theoretically, we can have pHs greater than 14. And if we get a strong enough base, we can see a pH of 15, 15 and a half. And if we have a strong enough acid and it's highly concentrated enough, we can see a negative pH, a pH less than 0. But for practical cases, we can argue that the pH runs from 0 to 14, but you need to know, because I'm a theoretician and I can't let you get by without hearing this from me, theoretically pHs can be negative or greater than 14. Now, we can similarly define a pOH as the negative log of the OH concentration, and so OH is 10 to the negative pOH. If I take this equation and then take the logarithm of both sides, and using the properties of logarithms, I get this very important result, that pH plus pOH is equal to 14 at 25 degrees Celsius. So notice what that says. If I know H plus, I can find pH. If I know pH, I can find pOH. And if I know pOH, I can find hydroxide. So if I know any one of the four, if I know any one of H plus concentration, OH minus concentration, pH, or pOH, I know all of them. We'll look at some specific examples of those calculations when we meet together in class, but those definitions are important for you to know. We'll go over those more fully when we look at some examples in class. Now, here is, again, that generic reaction we were looking at earlier between an acid and a base. In this case, we're letting water, our solvent, be the base, and that's going to give us hydronium. Again, let's look. That's water plus a proton, and HA goes to its conjugate base. That's HA minus a proton. So one of them picks up a proton. That means this is a base, and one of them donates a proton. That means HA is my acid. The equilibrium constant for this reaction is called a Ka, and this is an acid dissociation constant. And again, it's still just products over reactants, and every time it's a 1-to-1-to-1 ratio. The beautiful thing about this is that the stoichiometry is simple. It's 1-to-1-to-1. Again, remember, we don't need to worry about the concentration of water because it's a pure liquid, and therefore its molar density, does not change. Now, in this context, you need to know what are called the strong six acids. The strong acids, there are 6 of them you need to know. Hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, that's one you may not have heard of before, and sulfuric. It's important for us to notice that for sulfuric acid, it's only going to give up 1 proton. Sulfuric acid's strong equilibrium then is going to look like this. Hydrochloric acid plus water is going to give me hydronium, H3O plus. We also write that H plus the hydrogen sulfate or bisulfate ion. Okay? There is that equilibrium specifically for sulfuric acid. Now, here is the important thing. For these strong 6, for the strong acids, the Ka is greater than 1,000. Okay, remember our discussion of large equilibrium constants. What does that mean? They completely dissociate to form hydronium. So for strong acids, the equilibrium concentration of hydronium equals the original concentration of the acid. So at equilibrium, hydronium concentration is essentially going to be the original acid concentration. So the pH, which is defined as the negative logarithm of hydronium, is equal to the negative logarithm of the acid concentration. Or if I know pH, I can calculate the concentration of the acid. You may have noticed that I have used these 2 terms interchangeably. Previous to this page, we had talked about the concentration of the proton, H+. We'll use that interchangeably with the concentration of hydronium. Here's what goes on in water when we have a proton. It finds water and it forms hydronium. Hydronium is the actual species that we find in an aqueous solution, but it's just very much simpler to write H+. I will use it interchangeably. I'll be honest with you. In high school, I was first educated with H+. When I got to graduate school and got deep into theory, it just felt more comfortable to me to write hydronium. So I will almost always write hydronium when we write the equilibrium, but you may have been raised with H+, and that's fine. Again, these 2 are going to be used interchangeably. Just remember, if you see one, you're seeing the other. So let's look at a couple of examples. Here again, here's what we know. But for the strong acids, the equilibrium concentration of hydronium is equal essentially to the initial concentration of the acid. So the pH can be found just by taking the negative logarithm of the acid concentration. So here we go. What is the approximate pH of 0.0422 molar HCl? Well, we recognize HCl is one of the strong six, and so the pH is just going to be minus the logarithm of the acid concentration, or we get a pH of 1.375. Notice that's less than 7, so the solution is acidic. Well, that's good because this is hydrochloric acid. That's stomach acid. This concentration of acid is actually weaker than what your stomach acid is, so the pH of your stomach is even a little bit lower than this. But we get a pH of 1.375. That tells us we either have a very highly concentrated acid, which we don't, or a strong acid if the pH is that low. Now, I have to say one other thing from a mathematical standpoint. Notice that 0.422 has 3 significant figures, so I get to report 3 places past the decimal. That's how logarithmic math works with regards to significant figures. Now let's do the other problem, and one that's really a little more real world, where we would use a measured pH. We pull out a pH meter. You've done that. You've used the pH probe in the lab. Okay, we pull out the pH meter, we stick it in the solution, and we read a pH. So the question is, what would be the approximate concentration of nitric acid if we had a solution with a pH of 2.99? Okay, well, let's go back up here to the top, and let's say, okay, great. If I know pH, I can calculate acid concentration. So the acid concentration is going to be 10 to the negative pH, or 10 to the negative 2.99, and so we're going to have 0.00102 molar nitric acid, or 1.02 times 10 to the negative third molar nitric acid. So again, if I know the concentration, I can calculate pH. If I know pH, I can calculate the concentration. We can do the same sort of calculations with the strong bases. Now, the strong bases are going to fall into one large category, which is very simply the soluble metal hydroxides. Those are going to be the group 1 hydroxides, lithium, sodium, potassium, and barium hydroxide, along with one other I neglected to type in. The other soluble hydroxide is going to be ammonium hydroxide. Again, that is ammonium hydroxide. You're used to seeing these. You've seen sodium hydroxide in your all of your chemical life. Potassium hydroxide is also well known. Now, these soluble hydroxides also completely dissociate. So this reaction, sodium hydroxide, it dissolves from NaOH solid to NaOH aqueous. It dissolves, and then the NaOH aqueous completely dissociates to Na plus aqueous and OH minus aqueous. And so what we have, all of that to say this, the equilibrium concentration of a hydroxide is essentially the concentration of our base. And we can find POH if we know hydroxide, because we know the base concentration. Or if I know the POH, I can calculate the base concentration. Now, our pH meter is always going to give us pH, but if I know pH, I can find POH because pH plus POH is 14. We saw that on an earlier slide. That comes from the Kw, the autoionization of water. So a couple of other quick example calculations here, and we'll be done with this introduction to acid-base equilibria. So we ask, what is the approximate pH of 0.0422 molar potassium hydroxide? Now, because KOH is a strong base, that's a group 1 hydroxide, the POH is going to be the negative logarithm of the base, and pH is going to be 14 minus POH. So POH is going to be the negative log of 0.0422 or 1.375. pH is going to be 14 minus POH. 14 minus 1.375 is 12.625. Notice that is greater than 7. So indeed, this is a basic solution. Notice that doing pH calculations with base requires one more step than doing the acids. When we're in the acid calculations, we're in what I call the pH domain. In acids, it produces H plus, hydronium, and so we can calculate pH directly. Bases are going to, in aqueous solution, produce hydroxide. Hydroxide leads us to POH, and then with POH, we can then calculate pH, as we have done in this last step. Let's do the other way, and again, what's the approximate concentration of sodium hydroxide if the solution has a pH of 10.99? So let's notice, again, if we know the pH, I can know the POH. Again, remind yourself, pH plus POH is equal to 14. So if I know pH, I can find POH. POH is going to be 14 minus pH. So we calculate that. So the pH was 10.99. 14 minus 10.99 is 3.01. And then my base concentration is going to be 10 to the minus POH, or 10 to the minus 3.010, or a concentration of 9.77 times 10 to the minus 4th molar. Notice that it does not take a strong concentration of sodium hydroxide to give us a fairly large, nearly 11 pH. This concludes our introduction into acids and bases, strong bases, and pH and POH calculations. Our next video will look at what we call the weak acids and the weak bases. These are ones that are only going to dissociate with water slightly. In equilibrium terms, they're going to have very small equilibrium constants. And so we'll also come up with a dedicated formulaic way of going back and forth between the concentration of acid and the pH, or the concentration of base and the POH, and thus from there the pH. And we'll take that up in our next video.